Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, I'll help get you started with Class 16 on confidence intervals with bootstrapping. We'll be looking at this QMD file, so let's go ahead and save that link to your working directory, and we'll open it up in RStudio. And we will render it. Okay. Your result may have just popped up. For me, I need to go to that folder and open the file. Okay. So we've got two case studies from Chapter 12 from the IMS2 book. So let's go ahead and open up that link. Right. There we go. All right. So we're going to make confidence intervals, right? So a confidence interval is not what we wish it was. It's not the probability, like it doesn't represent an interval that gives us the probability where the true population is in that interval. It would give us that if we were Bayesian statisticians. In this course, we are using frequentist methods. There are at least two schools of statistics. And in frequentist methods, the parameter in the population is fixed, and we have an interval that we're going to construct conditional on the data that we observed. So it's the interval that's random. And so the procedure that we're going to use for generating the interval has a 95% probability of correctly containing the true population parameter, because each sample that we draw will construct an interval, and it either contains the interval or it does not. And so you're either right or wrong, and you don't know which. And there's no way to know, because you don't know what the population parameter is. Okay. Practically speaking, the interval that you get from a frequentist analysis is an approximation to the Bayesian interval. So it's not completely wrong to say that you've got a certain probability of the true population parameter being in the interval, but it is actually wrong. So we will not say that. All right, let's take a look at this first case study, medical consultant case study. So people providing an organ for donation sometimes seek the help of a special medical consultant. These consultants assist the patient in all aspects of the surgery with the goal of reducing the possibility of complications during the medical procedure and recovery. Patients might choose a consultant based in part on the historical complication rate of the consultant's clients, right? So you're going to go to someone for this organ donation, and you want the doctor you go to, hopefully, to have a low rate of complication. All right, so in this example, we've got data. One consultant tried to attract patients by noting that the average complication rate for liver donor surgeries in the U.S. is about 10%. So that's like the population average. But her clients have had only 3 complications in this 62 liver donor surgeries that she's facilitated. So that is going to be a bit lower if you divide 3 divided by 62, lower than the 10%. She claims that this is strong evidence that her work meaningfully contributes to reducing complications, and therefore you should hire her for your surgery. All right, so let's get conditional on her data, right? Now, the 62 liver donors that she's performed is a sample of all possible liver donor surgeries that she could perform. Therefore, we're going to use this information as an estimate to give us a confidence interval for where her true population parameter percent of complications lies. Okay, so all right. So let's, I've assumed that you've read through this chapter. Her estimate is about 0.05. Okay. All right. All right. So I think somewhere. Oh, maybe it's in the summary near the bottom. Give me a second. I just want to point out where I'm getting information from. The chapter review. Okay. Down at the chapter review summary, it talks about randomization and for calculating these confidence intervals. Right, we're still in the non-parametric randomization methods. I think starting maybe next week or the week after, we're going to start using parametric tests like what you would have seen in introductory statistics with a t-test and a normal distribution test for proportions, things like that. All right, so here is what we're going to do. We're going to frame the research question in terms of the parameter to estimate. Primarily, we're going to define what the estimate is and what the parameter is. Okay, then we're going to collect data. Okay, we will have the data already. Model the randomness by using the data values as a proxy for the population. So this gets into the idea of what the bootstrap does. This is the main topic of this video lecture. Once you have that random sampling distribution, the bootstrap sampling distribution of your statistic, then you can construct a confidence interval from that and make a conclusion. Now, our conclusion in this case is going to be, is her complications rate less than the population complication rate? It's actually they've done a strange thing in this chapter. They have we're basically using the confidence interval to do a hypothesis test, which is okay because they usually agree, but they don't necessarily agree in all contexts. Okay, so let's talk about the bootstrap procedure a bit. All right, is this where they talk about it? The variability of the statistic. Let's see if I search for bootstrap. Okay. The bootstrap is a procedure that I use all the time. I was just an expert witness in a court case, and I used the bootstrap extensively throughout the work. So the idea is that there's a population out there. So here's a population on the left, and from there you've drawn one sample. And from that sample, in this case, we've got, the proportion of complications is the statistic or the parameter that we're interested in. If we could measure every observation in the population, or every experimental unit, every unit in the population, then we would conduct a census. We would have no uncertainty because we've measured everything, and we would know exactly what the proportion of complications is in the population. That's the parameter we care about. It's often unfeasible or impossible to measure every unit in the population, so we collect a sample, and from that sample we're going to make an inference about what we think the proportion is in the population. Okay, so the basic idea of the bootstrap is if our sample is representative of our population, then we can perform a bunch of resamples from our sample. Okay, that's not a great, even this is sort of lacking what we wish we could do. All right, what I want is a slightly different picture. Okay. Okay, we care about what the sampling distribution is of the statistic given the sample size. That's basically the idea, and the sampling strategy. We'll just assume that we have a simple random sample. So we've got this whole population on the left, and if in this case we've got samples of size 7. Okay, so if you take samples of size 7 over and over and over again from this population, each of them will provide an estimate for the proportion, in this case, of red dots. Okay, so we're calculating the proportion of red dots here. This is 3 over 7. So if you do that over and over again, for different samples from the population independently, you will get different estimates. Sometimes you'll get 4 red dots, sometimes you'll get 7 red dots, sometimes you'll get no red dots. But typically, the sample you get will give us a proportion of red dots that are consistent with the global population in the population, the global proportion in the population. All right, so we wish we could do that an infinite number of times from the population so that we had a sense of what the true sampling distribution is. But it's only feasible to collect one sample. In practice, if you could take more than one sample, you would actually combine all of those samples together so you've got one, big sample, because that's going to give you your best evidence, right? So we still only have one sample in a sense. Okay, so how do we get the sampling distribution of our statistic if we can't take multiple samples from the population? The answer is the bootstrap. The bootstrap is a strategy where we assume our sample is representative of our population. That is the key assumption. If our sample is representative of our population, then we will treat our sample as though it is a population. Okay? Did they've got an example that I like? Not quite. So the sample is representative of the population. From there, we're going to draw many resamples. The resamples are the ones that the samples that we wish we could take from the population. Instead, we're going to take those resamples from our sample. And from each of those resamples, we can now have the amount of times we have 2 reds, 4 reds, 5 reds, and so on. And now we've got a sampling distribution of the number of reds in our samples of size 7. And we can then use that as our sampling distribution. And finally, so we'll use the sampling distribution then to say where is the central 95% of our sampling distribution? Where does it lie? In this case, it probably lies somewhere between, say, 0.2 and 0.7 or something, roughly. Okay, and that will give us our confidence interval for what the true proportion of reds is in the population. All right. So the big idea here we go. This is the resamples from our sample. So the big idea is we are not going to make any assumptions about the sampling distribution. Often the sampling distribution is assumed to be normal for proportions, or a t-distribution for the sample mean, things like that, a chi-square distribution for the variance. But rather than making a distributional assumption, we are going to generate the sampling distribution from the data itself. Okay, so let us go and do that. Okay, so through this process, we've actually walked all the way through the study that we're going to look at. Okay, so here's the medical consultant case study. Let's go over to R and start working on this. Okay, how come those stars don't light up, but these do in blue? Oh, doesn't matter. All right, so we'll start by making sure that we've downloaded the file, we've opened it. Oh, you've already knit it, right? Have I? Have I rendered it already? I think I have, and we're looking at it over here? Yes, okay. Sorry, I've forgotten already how much we've done. All right, so we'll load the packages, and then we'll start looking at the data. All right. Okay, so the data here, now I've spread this text out. There's a much more compact form you can do this, but I'm creating a table. Modern version of a table is called a tibble, and in this table there's going to be a column called outcome, and where I'm going to have replications where here, let's just run this little piece of code. Okay, so I'm going to repeat the text yes complication 3 times. So here's that result, 3 yes complications. And then I'm going to do this for no. So I've got 62 minus 3, or 59, no complications. All right? And then I'm basically going to recode this as zeros and ones because it's going to make it a little easier for calculations. So if the outcome is yes complication, make this second column complication equal to a 1, otherwise make it a 0. Okay? So if I run all of this and look at the data set, I've got outcomes yes and no, and ones and zeros. Okay? And if we look at a table, you see that the zeros for complications line up perfectly with no, and the 3 yeses are ones. Okay, so I can use either of these columns for the analysis. There's our data. All right, so that's the first part. All right, frame the research question in terms of parameter and estimate. Looks like I've done this for you. So the parameter is the true proportion of complications in the population, and the value of that is 0.10. And the statistic is what we've calculated from our data. It's the observed proportion. So that's 3 out of 62, or, almost 5%. All right. The variability of the statistic. Here's the main part. All right, so let's make a code chunk. All right. Similar to last video, we're going to do some randomization. So the number of replications, let's start with 10, and once we have more than that, we will, once we get it working, we'll increase that number. We're going to make a loop. Oh, you know what? Let's just sort of do some pseudocode first. So for, say, 10,000 times replications, we're going to, we need a place to store the results. And the results we're going to store is, we're going to randomly sample or resample from the sample of complications. Okay, and then we're going to calculate the proportion of complications, and then we're going to store those results. I think that's it, and then we'll plot a histogram of the bootstrap sampling distribution. Okay, so let's find a place to store the results first. Let's call this simulation for P, for proportion. And just like last time, I'm going to repeat NA reps time. So if I have run reps equals 10, then here is the starting sim P to store the results of the simulation. All right, so then I'm going to use a for loop for I reps in the sequence length of reps. And we've saw this last time. The sequence length of reps just goes from 1 to 10, because that's what reps is. Oops, there we go. All right, we begin our for loop, and we end our for loop. All right, we'll indent. So now we've got to randomly resample. So what's our data here? Dat medical. All right, there's our data, and we can use the complication column of zeros and ones. So if we start with this, then, oops, I don't know why that came up. All right, we're going to use the sample function again from the base package. And the main idea here is that we're going to sample, but with replacement. If we didn't sample with replacement, so each time you sampled one of these values from the complication column and didn't put it back, and we sampled 62 of them, well, you just get your sample back, just in a different order. But the order doesn't matter here. So we're treating our sample like a population, as though it was, infinitely many copies of this. And so when you sample one observation, it doesn't really diminish the infinite number of observations that are possible to collect from the population. So for that reason, with replacement is the strategy we're going to use here. So we're going to start with our data, and then we're going to sample, and we'll do replace equals true. Okay, so let's see what that looks like. Well, our original vector of numbers had 3 ones at the beginning. This one happens to have also collected 3 ones. Let's run it again. This one has 1, 2, 3, 4 ones. Okay. This one has 1, 2, 3, 4, 5 ones. Okay. So you can get different numbers of ones each sample. That's exactly what we want. Then we want to calculate the proportion. So we saw this last time. If you then pass that list and you add them up with the sum, that's going to count the number of ones. Okay, so if we run this over and over again, we've got different numbers of ones each time. But we want the proportion. If you calculate instead the mean, then it's the total number of ones divided by the total number. So now we've got proportions. And we want to assign the result of that to the iReps position of our vector, so that each time we go through, we'll put it in the next position. SimP, the first position, will be the first sample, then SimP2 will be the second position, and so on. Okay, so we've randomized and calculated the proportion. So I'll sort of put those two comments together, and let's run this whole thing and take a look at SimP. There we have 10 proportions. And then, let's see, SimP, if we put that out to a histogram and look at it, there's our sampling distribution. Now we really need to increase the samples, so let's do that. Okay, it doesn't take long at all. We have this right-skewed distribution, which is beautiful. This is exactly what someone who really understands the binomial distribution would expect the shape to be. For the sampling distribution, this is perfect. Okay. Have we finished this part? Variability of the statistic. I think so. This is the sampling distribution. So perfect. We've got SimP, which are all of the proportions. Okay, step 3, calculate and interpret a 95% confidence interval. All right, so I say in a simulation of 62 patients, about how many would we expect to have had a complication? All right, so if we're looking for the central 95% confidence for this, we want to, so how many values do we have? We have reps. So we have to come in 2.5% from one side and 2.5% from the other side. And that will give us 5% left on the outside, and that therefore our central 95% is in the middle. So we're going to basically count in from the left and count in from the right. How many do we need to count in? So let's see, there's lots of ways to do this. I think I'll go sort of a slow way to help you sort of think about this. So we've got the index of the lower and the index of the upper. Okay, the first thing we need to do is sort our data. So if you take our data and sort it, then, let me see if I can scroll up here. There's a whole bunch of zeros. There's a whole bunch of times when you get 0 complications in our sampling distribution. And then you start getting a bunch with 1 complication, which are these numbers here. And that goes on for a while, beyond 1,000. Okay. You know what? Let's turn this down a little bit to maybe just 1,000 observations or 1,000 replications instead of 10,000 at the moment. That way we can actually get all of the values on the screen. okay? Because at least for my system, 1,000 is the default. Oh yeah, so if we take that and we sort them, okay, then we've got some zeros, we've got 1 out of however many, and so on, up to whatever this number is, 16 out of, 0.16. If we take that and multiply it by, is it 62? Okay, so 10 complications is the maximum that we've observed. Okay, so what we have to do, we've got 1,000. Reps is 1,000. Okay, so if we want the middle 95% of this distribution, then we need 2.5% left out from one side and 2.5% left out of the other side. So our index, if we're counting in from the left, is going to be reps times 0.025. Okay, so let's take a quick peek at this. So that's going to say that you, out of the 1,000 replicates, we're going to count in 25, and that's going to be our lower bound. Our upper will be similar, and I'm not going to worry too much about exactness here. I'm really just focusing on the main ideas. Okay, so then we've got for the upper, the rank ordering will get us to the 975th observation of this sorted data. So where's 975? Here's 974 is this one. So the next one is 975. That would be the right boundary point for the right side of our confidence interval. Okay, so about 11%. So I'm creating these two indices, in for lower, in for upper, and now we just need to extract those two positions. So how about P, the confidence interval? That's going to be, well, we're going to have two numbers, so we're going to combine them into two numbers. First, we're going to sort the sim P, and then we're going to pull out the index of the lower. Now, this is an inefficient algorithm because I'm doing the sort twice, but I'm also not storing it. So anyway, so we've got, so each of these, so we've got 0 and 11.11. Okay, that's what we saw before. It was this one here. Okay, if we save both of those, then and print it out, we now have those two numbers. And there's a cool thing you can do. You can actually label these if you wanted to, lower and upper. And if you do that, you actually get labels on the numbers. So anyway, that's well beyond what we needed to do. So let's write about how many we would expect in the population. So we've got, let's see, we are confident that in the population, the true probability or proportion of complications is between, and then we're going to print out these two numbers, which means I better print it out down here because I need to perform the calculation first. All right, so we want to print out the confidence interval, the first one and the second one. So we'll do, we'll make a little R calculation here. We're going to print out P underscore CI, and we're going to do the first one is the lower, and to 3 significant digits. Let's see what that looks like. Sure does. Looks like 0. And the upper bound is the second index. Oops. If we look at what that is, 0.113. Okay. Period. All right, so we're confident that the true population is somewhere between here. The word confidence here is doing a bit of work because, as I was saying before, the true interpretation of a confidence interval is that it's the process leading to the confidence interval before you observe your sample data that gives you a 95% chance of your interval containing the true parameter. So you're making a prediction based on the procedure, and the randomness is in the data collection. Once you've collected your data, there's no more randomness. You've constructed an interval, and it either contains the true population parameter or it does not. There's no more randomness. Therefore, there's no more probability. It either contains it or not. You just don't know if it does. So, you know, there are better interpretations of a confidence interval, I'll just say. Okay, so is the consultant's rate statistically lower than the national rate of 10%? Now, we actually should be conducting a hypothesis test here and not a confidence interval, but we can answer that too. I believe if we go to the chapter, this question is answered somewhere. Okay. Is the original claim that it was less than 10%? Okay. Here is the answer. Okay. It's no, because the interval overlaps 10%. It might be that the consultant's work is associated with lower risk of complication, or it might be that the consultant's work is associated with a higher risk. Okay, that's possible too. Additionally, as previously mentioned, because this is an observational study, even if the association can be measured, there's no evidence that the consultant's work is the cause of the complications rate being higher or lower. It could be that you live in a place where there's more healthy people, so their outcomes are better than living in a place where there's people whose health is worse, you know, basically higher and lower socioeconomic status, that sort of thing. And that's it. We did it. So let's make sure that all this works. And the other thing we can do is we can up the reps to 10,000. I'm not going to rerun it just for this demonstration. Let's reload this. And here's our code. Here's our histogram. 1,000 I think is sufficient, but 10,000 will make this look slightly nicer. Here is our confidence interval. It will be different each time you run it, potentially, depending on how, you know, what the actual shape of this distribution is. The variability of these bounds will certainly decrease as the number of reps increase. Okay. And finally, do we have, yes, we're confident that, and here's the numbers that come from here in our text. Perfect. So with that, I believe you can complete the second example. Let me take a quick peek at my answers to see if that's true. Oh yeah, for sure. This one's not very challenging. So if you follow that example, you will be successful in the second half of this assignment as well. All right, see you in the next one.